Bismillahirrahmanirrahim. Welcome back to my channel. This video is going to be on wireless communication signal propagation. I think I already made a video on it and where I discussed two-way model, which is the most common model that we normally use to understand the wireless propagation in free space, where I have my ground as acting as a perfect reflector. Building upon the same thing, as we know that multipath fading is that you have multiple paths that is bouncing off from different places, and you would receive a copy at the receiver end, and if they are constructively added together, they will either have the signal present or they can just completely diminish your signal. You won't receive anything. So this model is actually a depiction of that, building upon the same simulation that we have done for two-way model on GnuRadio. So these are a few terms that you need to know regarding this particular 10-way simulation. What 10-way simulation basically means that I have a transmitter and a receiver, I have a line of sight link, and then I also have a link that is ground reflected link. These are basically the two-way model that we looked at. You have a line of sight link, LOS, then you also have GR, which is your ground reflected link. Then I added, then this simulation added a couple of other things. For example, we have a SW, this is a single wall reflected, so this is being reflected from the wall, so SW is single wall detected. Then you have double wall detected, which means it's bouncing off from, so it bounces off from this wall, goes to this wall, and then it bounces off like this. And then you have a triple wall reflected signal. You have TW signal that is transmitted, hit another wall or a ground, and went back to another wall, and then back to another wall, and then being received here. And then you have a wall ground reflected signal that is being bounced off from the wall and the ground. Then you have a ground wall reflected path, and these are different paths which are available to us. So that's how the simulation is. So you have actually basically you're receiving, due to the reflection in the environment, you're receiving actually 10 copies of the same signal, and how they are going to get added constructively and destructively. So basically this is the flow graph. Same type of calculation has been run. You have an antenna gain. Since you have a single antenna, you have an antenna height, you have an antenna gain. Then of course you will have a distance. All of these distances, just like in two-way model, we calculated the distance. Ground reflected distance, which is going to be based on LOS delay. And of course we will have then wavelength calculation, similar calculations that we have done for two-way model. This is just a build on the same concept. You have a distance between your transmitter and receiver that is from 10 to 15 kilometer. You have a wavelength, so we're working with 900 megahertz. Same thing, wavelength is calculated, lambda is equal to C over F. Psi pi constant value C, which is speed of light divided by frequency, that is your wavelength. And these are the couple of things that is added into this flow graph. Just like the same simulation that we have done, we have a signal source, then the delay block. Delay block is taking an integer value of line of sight delay times the sample rate, and this is that line of sight delay. Line of sight delay basically line of sight distance divided by a constant C based on the two-way model equation. Same thing for ground reflected delay. Then you have a single wall delay, then you have wall ground delay, and then you have double wall, and then you have triple wall. These are the things which are incorporated here into these delay blocks. These delay blocks are incorporated using these delay parameters that we're using, and everything is being multiplied by a multiply constant block. If you remember this equation was actually 4 pi d squared. So let's look at the equation. Wavelength divided by 4 pi, line of sight distance. This is going to be ground reflected distance, then for double wall, for single wall, and this is how the antenna is. So basically this is the first equation that we have used in two-way model. We're using exactly the same thing. The only parameter that is changing is actually this LOS distance for this. Let's look at the second multiply constant block. This is for ground reflected. This was basically, these were the only two things which were present. Then you have a multiply constant block for single wall, and so on. All of these signals are being added together. All of these signals are being displayed here in that GUI block, and all of these signals are being added here as well. So all of these signals are going into an adder, and this adder, after adding those signals, that is coming out as an output to this GUI time sync, which is your oscilloscope. And in this way, we can visualize all of these signals. So this particular signal is the addition of all of these two signals at the receiving end. And these are the individual signals which are being received by my receiver. And this is also by my receiver. And we can individually monitor those signals as well. So by changing the distance and by changing the frequency, we can actually visualize where my signal is being added constructively and where they are being added destructively. You can also watch my other video on two-way model, which actually describe these blocks in detail. But this is just to show that indeed you can apply it for multiple ways. Because in wireless communication, we have multipath propagation, and we don't know how many paths are going to be there. The only thing that we are sure of, we can just simply ask ourselves using probability that what percent of the signal, if I transmit this much, I will receive in terms of probability. So let me run this simulation. The simulation is quite simple. So we have line of sight link. So this is you're getting maximum signal. You have ground reflected signal, which is at in green, in red, and then you have a couple of other signals. And this is the combined signal that you're receiving at the receiver. So let's look at that combined signal. If I were to just look at it, so this is what we're receiving. If I have line of sight link, then you have something that is being reflected from a single wall, from wall to ground, then double wall, and then triple wall. This is how much signal that you would receive if you're transmitting at 900 megahertz and you have a distance of 10 meters. So this is probably the signal strength that you're working with. This is the signal that you would receive. Now, if it's destructively added, it will completely diminish that signal. So by changing the distance, you can also vary this. So by just changing a little bit, this is how much we're seeing at the receiver end. This is the combine of all of these. So all of these are added together, and this is what we're seeing if we are at 280 meters. And this changes up to 15 kilometer. So we're looking at about 3.2 kilometers and things like that. So let's just leave this at about 380 kilometers. And by changing the frequency, you can also see the effect of my constructively added signal and my destructively added signal. So let me just move this a little bit. Let's change the frequency and let's see if I can see the change. I think my flow graph was stuck. Let me just run this simulation again. Let's change the distance. Let's say 410, and let me change the frequency. So you can right here at this point, you can clearly see. Let's look at our combined wave. Because most of these things are canceling out each other, that's why you see a signal strength of my combined receive signal at the receiver is going to be this, because most of them are like canceling each other out, or some of these are canceling each other out. By changing the frequency more, okay, now let's look at my combined signal. This is the combined signal. You can see that there's an increase in my signal. So my signal at 410 meters and about 1, 2, 3, and I think my frequency is up till 512 gigahertz. So we're looking at 3 kilo, so we're looking at about 1.2 gigahertz. At 1.2 gigahertz, this is what I'm seeing. Let's change this frequency a little bit more, and let's see our combined signal. So this is the combined signal. So this is being added constructively. Let's change this frequency more. Let's say I can completely diminish that signal if I can. No, I still cannot. Let me just change this to a little bit more. Can I? Because you have to go really slow on this. Alright, let me just increase my. So this is probably the smallest that I can find in terms of my received signal strength. After 10 different waves are being reflected from everywhere, and this is the type of signal strength that I would encounter in terms of power. So this is how much power that is going to be received. So this is somewhere around in a picowatt value. So my signal strength is quite down, and picowatt or nanowatt corresponds to roughly, I'm saying roughly, somewhere around -100, -100 dBm or something like that. So this is the best way to visualize your multipath fading using GnuRadio. And if you have any questions, leave it in the comment section. And don't forget to like and subscribe to my channel. And go to my GitHub. I might be sharing the simulation there as well. So you gotta check out my GitHub page to actually download the simulation.